Hey everybody, it's Mr. Carr again. Today we're looking at 12.3 day two. We're continuing our ideas of instantaneous rates of change, but now we're going to be talking about it in terms of being an instantaneous velocity. Okay, lots of times we're just referring to something that has a little bit more context to it. Okay, so if the distance an object travels is given as a function of time, then the instantaneous velocity is this. Notice that that's our same rate of change idea, our instantaneous rate of change. So provided the limit exists, we're looking at this right here. We're just putting into terms of velocity and time, basically. So tourists standing on a 300-foot tall viewing tower often drop coins into the fountain below. The height of a coin falling from the tower after t seconds is given by h of t equals 300 minus 16t squared. Find the instantaneous velocity of the coin at 2 seconds. So we're saying that to evaluate this limit, so v of t is going to equal to the limit as t approaches 0 of, it'll be, well, h of t in this case. But if I look at what is h of t plus h, that's going to be 300 minus 16 times t plus h squared, and then minus my h of t, which is 300 minus 16 t squared. Whoops, t squared. Okay, all over h. So first thing I want to do is I want to distribute out t plus h squared. So it looks like this will be the limit as t approaches, or yeah, t approaches 0 of, sorry, not t approaches 0, h equals 0. My bad. Okay, we're doing it in terms of h here. So the limit as h approaches 0 will be of 300 minus 16 times, it'll be t squared plus 2th plus h squared minus 300 plus 16t squared all over h. Let me write this part a little bit better. What? Plus 2th. Okay. Distribute the negative 16 here. So this goes to everything. So the limit as h approaches 0 of 300 minus 16t squared minus 32th, whoops, minus 16h squared minus 300 plus 16t squared all over h. Okay, so from here again, like we've done with our previous limits like this, start canceling out our common terms so we can get rid of negative and positive 16t squared, as well as 300 and negative 300. So the limit as h approaches 0 of negative 32, you know what, might as well just do it here too. I can cancel out the h's like this. So I'm just left with the limit, rid of that. Okay, I'm left with negative 32, boy, negative 32t minus 16h. Okay, and then since we're evaluating as h approaches 0, that means my velocity function is given as negative 32. Did it again, negative 32t. So we want to find the instantaneous velocity of the coin at 2 seconds. We're saying, what is v of 2 now? Well, v of 2 is going to equal to negative 32 times 2, which in this case comes out to a negative 64, and that's going to be feet per second. Okay, so that's what we're looking at here is with our instantaneous velocities. Okay, so if we're moving on to our next one, the distance a bumblebee flies along a path is given by p of t equals 12t minus 6t cubed plus 1, where t is given in seconds and the distance is from its starting point is given in inches. Okay, so find the equation for the instantaneous velocity of the bumblebee at a point at any time. This one's going to have a lot going on. So we're going to go ahead and still do it like normal. Our v of t is equal to the limit as h approaches 0 of f of t, or in this case, p of t plus h. So it's going to be 12 times t plus h minus 6 times t plus h cubed plus 1 minus p of t here. So minus 12t minus 6t cubed plus 1 all over h. So we're looking at distributing the 12 and then expanding this out and distributing with the 6, as well as distributing the negative sign here. So this is equal to the limit as h approaches 0 There'll be 12t plus 12h minus, I'm going to go ahead and just do this as one big step, but remember, you're just doing through, well, here, I'll just do it as minus 6 times, it'll be t cubed plus 3t squared h plus 3th plus h cubed. Okay, and then minus 12t or then plus 6t cubed minus 1 all over h. Whew, okay. So now normally with these, okay, you'd want to distribute and start combining like terms basically. So we're going to take the -6 and distribute it to all of those. And remember, I'm just doing this as a shortcut. This is just coming from that. So you're just expanding that out, multiplying it out here. So the limit as h approaches 0 of 12t plus 12h minus 6t cubed minus 18t squared h minus 18th minus 6h cubed plus 1 minus 12t plus 6t cubed minus 1 all over h. And then we can get rid of, we got 12t's we can get rid of, we got 6t cubes we can get rid of, positive and negative 1 can be gone. I have an h, and then an h cubed. That's going to all go away there. So this equals the limit as h approaches 0. So what's left now is going to be 12 minus 18t squared minus 18t minus 6h squared. All right. Whew. Okay. Almost there. So now, again, because h is approaching 0, this really just going to cancel that out. It's going to be equal to 12 minus 18t squared minus 18t. Okay. And in this problem, all we want is the equation of the velocity, instantaneous velocity. So that means my v of t is my final answer. I don't like writing it there. I'm just going to bring it up here. My v of t in this case is just equal to 12 minus 18t squared minus 18t. That's what since that's what the limit is approaching. That's our instantaneous velocity for this given scenario. Okay, but that is yeah, that's it for today. You can try one on your own here, but the idea again is that our instantaneous velocity is basically evaluating the limit as h approaches 0 of a position function. So I had a position of the bumblebee here. I had the position of tourists, or the coin, sorry, not the tourist falling, the coin falling towards the ground here. So that's what we're looking at in terms of our limits, in terms of our instantaneous velocity and how it relates to position. Okay. But that is it for today. All right. Take care, everyone. So, sorry.